Okay, in this video we're going to look at a limit a little bit more formally, not quite as formal as perhaps some people get into it. We're not going to be using deltas and epsilons. But I've written up here an informal definition of what a limit is, and you can read it there. I'm not going to read it to you, but as you're reading it, I'm going to kind of graphically show you what this actually means. Okay, so all this is saying is if we have some function, and we'll call this function f of x. I just made a linear function here. Could be any function, could have been a parabola or some other weird graph. We'll just use a line because they're easy. If you have this function and you have a particular value of c that you feel like getting close to, and maybe this L, this random L up here exists. This is just a number. These just represent some numbers. Okay, as we get really close to that C, as I let the inputs for this function get really close to this value of C, I want to know what is my function doing. Okay, well, clearly as I get close to C here from the right hand side, my function is getting close or decreasing to this value of L. Okay, and if I jump to the left-hand side of C and I get close to C from the left, then you can kind of see your function is increasing in this case to the same number L. Okay, so what we could do then is we can actually write the limit as x approaches C of f of x equals L. Okay, so this is the notation that you should get familiar with, and I want to make a couple of points here. And probably the biggest one is this notation implies that you're approaching C from both directions. Okay, this limit only exists if, as you approach C from both directions, f of x approaches this same number. If f approaches a different number from one direction as it does the other direction, then we have to deal with that differently, and we'll talk about that more later on. Okay, so let's go ahead then and look at a couple of examples. The first example is going to be this equation right here. You can see that I've called it s of x instead of f of x. That's okay. Looks like a cubic equation here, but when you look at the graph of it, it kind of looks like a quadratic. So I call this a disguised quadratic equation, because even though it's cubic, it really looks like a quadratic equation. I guess if I wanted to be a little bit more precise, I guess it's a disguised cubic equation because it appears to be quadratic, depending on how you look at it. Okay, so you can probably guess what point I'm interested in here. You'll probably notice this little hole in the graph, and that's simply because 1 is not in the domain of this function here. So if you try to plug 1 into here, you'll get back an error if you did it on your calculator, or you could just see that you're going to be dividing by 0, and we know that we can't do that. So graphically, let's try to evaluate the limit. Okay, no cool little animations on this one. We'll just kind of have to imagine what's going on here. As I approach 1 from the right-hand side, okay, my f, or my y value, is approaching, it looks like 3. Okay, this is 3 right here. As I approach 1 from the left-hand side, it looks like f is approaching 3 from down below. So the graph tells me that as I approach this value, it looks like f is approaching 3. Now this is by no means a proof. It's just kind of evidence that this is what the limit might be. Okay, if we wanted to prove it, we would have to do some more analysis. Okay, let's jump to the calculator and see if we can't numerically confirm that this limit really is 3. And here's my function right here. I've highlighted it. Here's the graph of it. It looks very similar to the graph we just came from. And I want to get into the table, and I want to let x approach 1 from the left and from the right. Okay, so I'm going to let my x value take on numbers that get closer and closer to 1 from both directions. Okay, so here we go. 0.9, 0.99, 0.999 is definitely getting closer to 1 from the left, and you can see that my y values are getting closer to 3 from below. Okay, if we jump to the other side of not 2, sorry about that. There we go. And we get close to 1 from the right-hand side, you can see something similar happening. Oh, that's okay if I did 3 zeros. I meant to do 2, but that's okay. You can see that as we get close to 1 from the right-hand side, my y values are getting close to 3 from up above. Okay, so it appears both from the graph and the numerical analysis, it looks like our limit is 3. So we can write the limit of x cubed minus 1 over x minus 1 as x approaches 1. We see that that equals 3. Okay, so this is how we would write that. Okay, let's jump into the next example here. And we have an absolute value function. Okay, and you can see the graph right here. And you could probably guess that I'm going to be interested in this point right here at 2. So graphically, let's look at what this limit might be. As we approach 2 from the right-hand side, okay, it looks like my function is approaching 1. It turns out that it is 1. It turns out that it's the value of my function anywhere along this curve is 1, so we're not really approaching 1. I mean, we're at 1 the whole time. But we say approaching just to say consistent with our language throughout other examples. So as we approach 2 from the right, we approach 1. F of x approaches 1. As we approach 2 from the left-hand side, though, you can see that something different is going on. Okay, it looks like we're approaching a different number. In this case, we're approaching -1 down here. So graphically, it looks like as we get close to 2 from the right and from the left, it looks like we're going to 2 different values. From the right, we're going to 1, and from the left, we're going to -1. If we jump to our calculator, let me turn off this function. Okay. Oh, I needed to turn on the other function. Sorry about that. You'll see the table here. You'll see the table is giving us not what I expected because we're approaching 1 and I want to approach 2. Sorry again. So let's go ahead and let's input some values to get close to 2. We'll do 1.9, 1.99, and 1.999. And we'll jump to the other side, 2.1, 2.01, and 2.001. Okay, so you can see the numerical analysis here is showing us the same results that we looked at graphically. It looks like as we approach 2 from the left, we're getting a value of -1, and as we approach 2 from the right, we're getting a value of +1. Okay, so what does that mean? Well, according to this definition out here, as x approached c from both sides, it had to approach the same value, L over here, in order for us to say that the limit was that number. Okay, so since this approached 2 different numbers, we can say that the limit as x approaches 2 of x minus 2, absolute value of x minus 2 over x minus 2, we would say that equals, what do we say, 1 or -1? Okay, well neither. They're not the same number, so we say it does not exist. Okay, so there's a few examples that can help you get going as far as evaluating a limit graphically and numerically. And in the next videos, we'll look at an analytical approach to evaluating limits. See you then.